During this session, I'm going to be answering the question which I'm quite sure you've all been asking: why do nuclei decay? We're going to be basing this around the IB physics standards to show that we're going to describe the phenomena of natural radioactive decay. So we're going to be describing that in a little bit more detail. And we're also going to be trying to identify why some nuclei are stable and some aren't. I'm actually going to approach those in reverse. So first of all, why are some stable and why are some unstable? Well, it helps if we look at an overview. Here I have a graph which shows the relationship between the number of protons and the number of neutrons in a nucleus. And what we have here is shown is known as the band of stability. These are examples of stable atoms that exist quite happily, and there's no chance of radioactive decay whatsoever. Now let's look at this graph in a little bit more detail and just extract some useful points. So first of all, beyond a proton number of 83, all elements are unstable. They have the potential to give off radioactivity of some way. They want to be less than that. Okay? So they're in an unstable situation. We'll notice at the bottom end of the spectrum, to start off with, when we have protons which are quite small and have a value proton number of less than 20, the ratio tends to be 1 to 1. And as we get a bit higher up, then the neutron to proton ratio tends to increase and gets larger and larger as the size of the element or size of the atom proton number increases. We've got to think about the region above this belt has an excess number of neutrons, so they want to be able to get rid of some neutrons. That's why they're unstable. And the region below the belt has an excess number of protons. So therefore, for an element to get from a state of having an excess to being stable, they need to get rid of some of these protons and neutrons. And this is the driving force towards radioactivity and radioactive nucleuses, is because they want to get into a more stable state. Now there's a number of different methods which we can go through to get to a more stable state, and what's being given off for the different types of radiation. So we'll just think of it to start off with what's being given off and the change for the nucleus. So to start off with, one option which we could have would be to give off something which is known as alpha decay. Now alpha decay would emit an alpha particle, which is a helium nucleus. So that means it's made up of 2 protons and 2 neutrons, and they're emitted from the nucleus. An example of this would be to go from uranium to thorium with the release of alpha decay and some energy. Okay, so we can see, and this is quite an important thing to think about, is how this is shown. And what happens here is I can follow and track, because I can see that the atomic mass has dropped by 4 and the proton number has dropped by 2, which will give an indication that alpha radiation and alpha decay has taken place. Another option we have here is beta decay. Now this is normally a high energy electron, and what happens here is a neutron in the nucleus decays into a proton. So a neutron just becomes a proton, and at the same time as that happens, to make sure that the amount of charge is balanced, if we're creating a positive charge, we've also got to create a negative charge, and that negative charge is shot off. So an example of such decay would be when carbon-14 changes to nitrogen-14. So we have the same number of nucleons, but in this case the proton number has increased, and that's done by getting rid of a beta decay, a high energy electron. Another example would be gamma decay. Now what happens here is high energy electromagnetic radiation is emitted. Okay. So there's no change in particles, but what this is normally due to is just the nucleus changes shape into a more stable shape. So gamma radiation is emitted as a result of that. Now what we have here is the atomic number stays the same and the proton number stays the same. There's no change whatsoever, but energy is released from the situation. So those are 3 examples: alpha, beta and gamma. Later on, when we think about beta radiation, I'll consider an alternative here, but just for now I'm going to move on past that. Now, one of the ways we can show this change is by looking at things graphically. So if you think about the formula which you saw earlier on with the change from uranium to thorium, what we have here is the red arrow is an indicator that an alpha decay has taken place. As we can see, the number of neutrons in this situation has dropped by 2. The total number of nucleons has dropped by 4, and the number of protons has dropped by 2. And we've got a series of decays taking place here. So it's not that just one decay is going to take place and that's the end. Often with these larger particles like uranium, a whole series of decays are going to take place, and eventually it's going to get to a stable state. We can also see that on this diagram we can see some beta radiation. So the blue arrows indicate beta radiation, and in that case the number of neutrons has gone down but the number of protons has gone up. So that's the idea of radioactive decay, examples of radioactive decay, and the reason is because we have an unstable nucleus. It wants to be in a more stable state. Final question for you to think about. During beta decay, which of the following is true? A, atomic number increases by 1. B, atomic number decreases by 1. C, atomic number increases by 2. Or D, atomic number decreases by 2. Think of an answer. Hopefully you all picked answer A as the correct answer. That's the end of this session.